Good morning, friends. This is the beginning of a 40-week session for GATE 2027 aspirants. The students and faculty of SMAITM Bantakal have come together to create a forum, learning forum, where there will be weekly lectures at 9 a.m. for 1 hour duration on specific topics which are part of the GATE 2027 syllabus for computer science. Today's session is on discrete mathematics by Ashwin Rao. I would like to sincerely thank Ashwin for taking this initiative and time to study the subject and share whatever he knows with the team. For your information, the session will be recorded. Kindly ensure that we don't have any loose talk during the session, but all technical questions are invited. Over to you, Ashwin, and wish you all the best.
Sure, sir. Thank you, sir. Thank you for having me as a part of this series session. Good morning, everyone. I will be teaching you today when. Oh, let's go get into it. So today I will be teaching sets, relations, functions, partial orders, and lattices. For next, why discrete mathematics matters in GATE. Discrete mathematics is a foundational to the theory of computation, algorithms, DBMS, compiler design, and discrete mathematics. Why it is matter? Because these are the mass structure which is over a period of time observed in discrete mathematics in GATE. What you will learn from this end of the module is define and apply set operation, Venn diagrams, and set laws to solve the problems, and identify the relation properties using matrices and graph methods, and also classify functions as injective, surjective, or bijective, and compute compositions. Construct Hasse diagrams and identify maximal, minimal, greatest, and least uh, elements in posets. Compute LUB and GLB in lattices and differentiate distributive, complemented, and Boolean lattices. Solve gate PIQs confidently using shortcut methods and pattern recognition. So let's start with set theory. So what is a set? A set is a well-defined collection of distinct objects called elements or members. As you have learned in second year PUC, who have taken science as their optional subject, they have learned in mathematics about sets and all. The If you have forgot it, it is a set of well-defined set is a well-defined collection of distinct objects called elements or members. There's the real world analogy is a set of the examples are a set of students in a classroom: Alice, Bob, Carol. A set of primary numbers 2, 3, 5, 7, 11, etc. A set of vowels in English A, E, I, O, U, which is included in flower brackets. A set is also defined also by flower brackets, beginning the flower bracket, ending the flower bracket, and also elements in it or no any elements. The key notations include A belongs to A. This epsilon, like this weird symbol you see, right? This is epsilon. This says that A belongs to A. A, set A. This capital A represents set as equal to E. As you, if you have pen and paper, write a big capital A in it and equal to, then open the flower bracket or close the flower bracket. That represents the set. And also, what determinant A or n of A is the cardinality, number of elements in A. It represents, suppose I take this set, it contains how many elements? 1, 2, 3, 4, 5. It contains 5 elements. This is the cardinality, number of elements is represented. Then moving on to A, no, it does not belong to A. The element does not belong to A. If we define this set of primary numbers and this set of English, that both elements are different. If if this considers set A and this considers set B, the element of set A is does not belong to element of set B because these sets are different from each other. Then moving on to empty set, which is represented by this symbol. Null. This symbol is called as null, or the flower bracket beginning and closing with the no elements in it called as empty set, as I mentioned. There is two representation methods of sets. Two standard methods are roster method, tabular form, list all the elements explicitly inside curly braces separated by commas. Set example, set of natural numbers which are less than 6 are a is equal to 1, 2, 3, 4, 5. Set of even numbers b is equal to 2, 4, 6, 8. These are the these type of representation are called roster method. So what is the set builder method? Moving on to what is the set builder method? Set builder method describes elements using a property or rule format which corresponds to x or condition on x. Even natural numbers a is equal to x or x belongs to n and x is even. You can see in the roster method it is very hard to contain all the elements. So that's why for conditional properties and to represent sets in a very very uh, distinctive form, we include x belongs to n and x is even. These conditions we use. Similarly goes for all the elements 1, 2, 3, 4, 5 and all. And multiplies of c. If you consider 2's multiple, it considers x or x equal to 2k, where k belongs to n. So what is the tip I want to give in this is set builder notation is more powerful used to define infinite sets compactly. Both forms of questions appear in gate questions. So what are the types of sets? Moving on to this is the essential classification for gate. Empty set, which is contains zero elements. Singleton set contains exactly one element. Also, moving on to finite set, A is equal to 1, 2, 3 has a countable limited number of elements. Then moving on to infinite set, N, Z, R. These are have unlimited elements, which N corresponds to natural, Z corresponds to integer, R corresponds to real numbers. Universal set, which is represented by U, contains on the letter U contains all elements under consideration. So what? Moving on to power set. What is the power set? P function set beginning of the bracket capital A closing the bracket set of all subsets of A. This is the number of elements we represent. Please note it down because this is the important formula for if you count the subset of a. If you want to count a number of subset in a set. Okay, moving on to next.
Can you explain that
Subset
the PA? Can you explain the last power set? Can you explain, please?
PA, the last power is it is the notation for representing the subsets. Sir. Power set. P corresponds to power set. Subset. Set of all subsets of A, including null set and all.
So there is a set and it has many subsets. That overall
Yeah.
thing is called power set, is it? Hmm.
Yes. Yes. Where
Oh.
this that overall collection of subsets is called power set, and that formula is represented by 2 to the power of n. Here n corresponds to number of elements in that set.
So if there are three elements in a set, the power set will contain eight elements, is it?
Yes. Yes. Exactly, sir.
Okay. Okay.
Correct.
Including the null set. Hmm?
Yeah. Yes, sir. Yes, sir. Yes.
Okay. 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 Fine.
I'll clarify it, but sometimes it contains null set. I will let you know by the end of
Okay.
session. Okay. Then moving on to subsets and power sets, and yeah, it contains null set. Sometimes yeah, in superset sometimes it does not contain. Key formulas tested directly in gate. A subset A belongs A subset of equal B, every element of A is also element of B. Empty set is a subset of every set. That every set is subset is every set. Empty set is a subset of every set. Like in subset A also there is an empty set. In B also there will be an empty set. It is a subset that is commonly found in every set. Proper subset A subset of B. A subset of B, but A does not belong to B. At least one element of B is not in A. For this proper subset condition, there should be condition like there is an element. Example, B is set of natural numbers. A is set of natural numbers, but not beginning with 0. Um, B is a set of whole numbers. Sorry for the correction. B is a set of whole numbers, and A is a set of natural numbers. If we correlate the subset condition here, the 0 does not belong to natural numbers. Because of that, we can say that that 0 is that one element is not as the part of A element, so it will become proper subset. Then moving on to power set formula, if A has n elements, then proper subset of A number of proper subsets to the power of n minus 1. Why are we minusing the point is we are excluding the empty set as mentioned here. And then this is the proper subset
Sorry,
formula you.
proper set plus null set is equal to power set, is it?
Yeah, yes.
Okay, because the heading you have put is power set formula, but proper
Yes.
set is different, right? Proper set is power
Yeah.
set minus null set is called proper set.
Yes.
Okay.
Yes,
Hmm.
exactly. And if you want a shortcut to solve the problems, you can note down this formula. Yeah, if m n, then number of relation from A to B is to the power of m into n. So Venn diagrams and set operations, I will show this, but you can relate to this also. A union B, all the elements of A union B will be in that. If you consider A as a set of odd numbers and B as a set of even numbers, if you union that, there are the odd numbers and even numbers all are contained in that set, A union B set. X belongs to A union B if and only if you can ask what is the IFF. It corresponds to if and only if X belongs to A or X belongs to B, because one element of odd number is belongs to B, or A, if it is even set, then that element belongs to A. It can be either of them, but not both. The set should be different for union to occur, but some elements get cancelled, some elements get the places, but not every element is repeated in union set. Yeah, this is the like addition of the sets, but the records are kept intact. A intersection of B, intersection elements common to both A and B. Suppose consider A as set of all the letters in English and B is a set of vowels. Then what is the set of B in B? What is the elements which are common in B? A, E, I, O, U is common in also in English letter of 26 letters. That intersection is represented as A intersection B intersection. That set contains A, E, I, O, U, because that is the common occurrence in both of the sets. Here we denoting that A minus B difference elements in A but not in B. A minus B, but if similarly if we do B minus A also in which it corresponds to elements in B but not in A. Suppose odd numbers and even numbers. Suppose suppose I mention English letter words and be as a yeah, be as a ovals of English. In that letter, excluding vowels, you have to write all the letters of the English letters in this set, A minus B set. And what is A? Then moving on to A complement. Elements in universal set in U, but not in A. If I consider real numbers and irrational numbers, in that union contains all the numbers of the set, but it does not contain irrational. If consider A complement, if consider A as real numbers, universal number contains all the real numbers, but excluding the not A, consider A as relational numbers. Okay, in that, if you take the complement of that, it corresponds to irrational numbers. A complement, consider A complement as irrational numbers. How to derive the number of elements, or what is the set, is universal set of all numbers minus A. It corresponds to rational numbers. Both rational numbers and irrational numbers go to real number set. You can see A union B formula here. Number of elements in A, number of elements in B minus A intersection B elements is correspond to A union B. Similarly, this also. Number of elements in A, number of elements in B plus number of elements in C minus A intersection B, minus B intersection C minus A intersection C plus A intersection B intersection C. Here all the what determinant form you see, no, these are not the determinants. These are the number of elements that each set contains. Next. Please note these laws of set theory, as this is important for GATE, solving the questions in GATE. And any formula you see here, please note it down and practice it, because based on these, we will be solving the upcoming problems. Here's the De Morgan's law. Here's the associative law, distributive law, identity law, complement law, and idempotent law. If you don't don't memorize it, for each law you don't memorize it with the particular problem, you cannot understand the law, or with the current explanation you cannot understand. You have to solve the problems regarding to it. Okay, this is the solved problem set theory. This is the example problems. We will be solving VYQs, but for now let's solve this problem. In a class of 100 students, 60 study maths and 50 study physics, 20 study both. How many study neither? How to solve that? Consider M union P, where M corresponds to who study maths, and P corresponds to physics, who study physics, 50, minus 20 study both. M intersection P, students who study both math and physics, minus 20. 110 minus 20. 110 minus 20 corresponds to 90. Wow, who does not study neither? Like who studies chemistry, who studies biology, like that, equal to total minus M union P, 100 minus 90. What you can here see is this universal set, this total is universal set, that 100 total, you minus 90. Then you get 10. Who 10 student does not study both math or physics. Moving on to next question. If A equals to 1, 2, 3, find the number of subsets containing at least 2 elements. Okay. So this is the problem which we encode, which we formula. This it corresponds to this formula. Note it down. Please memorize it. How to solve this problem? Total number of subsets to the power of 3. Here 3 corresponds to number of elements, which is equal to 8. Step 2. Subsets with 0 elements. 1. Subset is 0 elements in 1 means that is the null set. I mentioned, right? That is the null set. Subset 1 with the 1 element is 3. 1. If we contain A as a proper set, singleton set, then it corresponds to 1, 2, 3. At least 2 elements it should contain. This is the 4 subset I mentioned, but at least contain 2 elements are 8 minus 1 minus 3, which is corresponds to 4. Here, note it down that at least 2 elements means it can contain it has to contain 2 elements. It can contain more elements, which is included in that. So that's why here it contains 1, 2, 3. Answer is 4 subsets. Okay, next question. Okay, here on Earth we are solving the PYQ problem. So let's get into it.
What problem? I didn't understand. Q and
Previous year question problem, sir.
oh, previous year question problem. Okay, fine.
Okay. Yes. As you can see in question, okay, first question is let A, B, C be sets. What is the A minus B intersection of C? Here you contain all of the above. Here you like okay. So this is the another problem. I will explain that. Okay, wait a minute. Okay, so you can see here. Let A, B, C be sets. A minus B intersection C. What it corresponds to? So as I mentioned and told you how to insert basics of set theory and all, A intersection C minus B, which all this all corresponds to elements number. So that's why it's mentioned all of the above questions because of that. This question answer is option D, all of the above. Which here you can see B complement, but this also a representation of set because of that.
Ashwin, we may not have time for previous year questions. So cover the
Yeah,
portions and let the previous
yeah,
year's questions become assignments for the people. Okay? Mm.
sure, sure,
Yeah.
sure.
Let it be in the
Okay, so
PPT. Let it be in the PPT always. But you
yeah,
cover the portions. Then if you have time, we'll go here. Okay?
sure,
We
sure,
will close at
sure,
10 sharp. Okay? Mm. Mm.
sure. Okay, I will cover the previous year question in document. I will assign it, and
Yeah, you
student
just put in
can
the PPT. That's enough. Okay?
yeah,
But cover
yeah.
the portions. Okay? Mm. Yes.
Okay, moving on to relations. Discrete this contains Cartesian product, relation properties, equivalence relations, and closures. Wait a minute, I need to mute, sir. Need some water. Okay, moving on to relations, Cartesian product, foundation relations and functions. A cross B, which corresponds to the set of all ordered pairs A, B, where A belongs to set A, and B belongs to set B. Example, A is equal to 1 comma 2 and B is equal to x comma y. A cross B corresponds to 1 comma x, 1 comma x, 1 comma y, 2 comma x, 2 comma 5. We are actually mapping the elements to the other sets and writing the ordered pairs. A cross B, A cross number of elements in A cross number of elements in B, 2 into 2, 4. This is the formula for finding the relations in the A cross B, number of relations. The matrix representation, as you can see here, 1, 2, 1, X, 1, Y, 2, X, 2, Y. The key properties include A cross B, but not B cross A. Because if you map the other way around, X, 1, X, 2, Y, 1, Y, 2. So like that happens. A cross B includes number of elements in A cross number of elements in B. As you can see here, A cross B corresponds to 4, where A cross B contains all the elements of 4. This is number of elements. Please note it down, this formula. This formula, A cross B, number of elements in A cross number of elements in B. Then corresponds to A cross empty set. This is equal to empty set cross A set, which is empty set. This is the common phenomena. As it is universally true across the relations and functions. This A cross B union C corresponds to A cross B union A cross C. This is the one of the key properties in Cartesian product and relations. Please note it down. Induction to relations. This is the Cartesian product. This is the basic for understanding relation and functions. So introduction to relations. Relation R. A relation R from A to B is any subset of A cross B. If A cross B belongs to R, we write A R B, where R corresponds to relation R. Binary relation R on A. A relation on set A means R belongs to or equal A cross A. Same set of both sets. Binary relation, it is set. 3 ways to represent a relation. Set of pairs R equals to 1, 1, 1, 2, 2, 3. This is actually interesting. The matrix representation 0, 1 matrix M I J equal to 1 if I J belongs to R. This is easy to check properties. Some type of problems comes with this also. You will rarely see these problems. If you see also, it's contained in set builder form and all. Directed graph nodes elements edge I, J if I, J belongs to R. Visual and intuitive. This directed graph you can get in advanced questions. We will solve all that. Number of relation on a set A with the number of elements A equal to N, where N is 2 to the power of N square. This is the number of relation of a set A which we can find out. Please note it down, this formula. Types of relations. Properties. The reflexive condition is for every set of A, for every element in A belongs to set of A, where condition is A, belongs to R. As you can see in example 1, 1, 2, 2, 3, 3 on set A, 1, 2, 2, 3. Here every element is a mirror image of set. This set 1, 1, 1, 2, 3. Every element relates to itself. That's why it's called reflexive condition.
How can you say mirror image? Mirror image is not correct, no?
No, sorry about mirror
Yeah,
image.
that is
It's
not correct. Every element is a subset of this element, right?
yeah. Correct.
Okay.
Sorry for the correction. Thank you. Okay. Then we go to symmetric relation. Condition is for every element in A, this is the every element symbol. For every element in A, comma B belongs to set A, comma B belongs to R, corresponds to B, comma A belongs to R. Like you can see in example 1, 2, 2, 2 is symmetric because you take 1 as A and 2 as B. which corresponds to 2 as 1, 2 comma to B as 2 and A as 1, which is symmetric, which contains.
This is almost like a palindrome kind of thing, is it? Mhm.
Yes, 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 yes.
Yeah.
Then it's also moving on to transitive relation. Condition is for every element in A, comma B, comma C in set A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R. Example, R is equal to 1 comma 2, 2 comma 3 and 1 comma 3 is transitive because the chaining method uh, A arrow B and B arrow C implies A arrow C. If you consider 1, 2, 3 as A, B, C, it implies 1, 2, 1 is 2 already mapped in set, 2 and 3 also mapped in set. Then 1 and 3 should also be mapped in set and should be mentioned. Okay. Then moving on to antisymmetric. The condition is for every element A comma B belongs to R and B comma A belongs to R, which represent A equal to B. Example, divisible root of n is asymmetric because every number can divide itself. That's why it's the set divisibility of n is antisymmetric. It's called. No, please note it down that symmetric and antisymmetric are not oppositors. A relation can be both only diagonal pairs or neither. This is the shortcut and matrix method. You can please note it down. It will be helpful to solve the answer also. Moving on to equivalence relation. The condition which I mentioned earlier, reflexive, symmetric, and transitive, which these three conditions are also satisfied when a relation satisfies all these conditions, then it's called equivalence relation. Equivalence classes for what that is the equivalence relation. If all the sets are if any set and ordered pairs satisfy all the reflexive, symmetric, or transitive conditions, it's called equivalence relation. Then moving on to equivalence classes. What is equivalence classes? For any element A belongs to set A, the equivalence class A is equal to X belongs to A. X are A. Classic example is congruence modulo n. A congruence P modulo 3 if and only if 3 or A minus B. This divides Z into three equivalence classes. As you can see here, these are the equivalence classes which corresponds to what is the mod gives remainder, no, that is mentioned here. Remainder when divided by 3, remainder when divided by 2. Multiple of 3 correspond to 0. Remainder 1 is defined as set, another set. 2 remainder gives 2, that is divided as another set. Here theorem is every equivalence relation partitions a set into disjoint equivalence classes, a partition of A. It will be partition of A. That's all. These are practice problems for
Skip
students who
this.
can.
Yeah.
Yeah, please go ahead. Uh,
No, you can skip the practice problems. Go ahead.
the get previous year questions also they can solve also. Moving on to functions. Okay, then introduction to functions. A relation where every element in A is mapped to exactly one element in B. The where A is considered as domain, B is considered as codomain. Range. Then F of A is actually considered as range. The key condition is every element of A must map to at least one element in B. Total function. No element of in A can map to more than one element in B, well defined. Well, this is the types of view functions that will give introduction to types of functions in later on session. Range is f of A is equal to this range is how determined is f of x, where x belongs to A, is a subset of codomain B. If A empty domain, F trivially a function, back S function. Types of function: injective, surjective, and bijective. One-to-one injective, distinct inputs give function distinct outputs. F of A equal to f of B corresponds to A equal to B. Example is f of x equals to 2x is injective because x contains x in every element contains is a multiple of 2. They can map also. On to is subjective. Every element of codomain has at least one pre-image in domain is to n equal to codomain. The example is z maps to z. F of x equal to x plus 1 is subjective. Many to one. Two or more elements in domain map to the same element in codomain. The example is f of x to
What
the
is
power
the
of
meaning? What is the meaning of codomain? I didn't understand.
domain is what is the main set we are considering to map to B. Map to here domain is what we consider A. Example, take element set A, which contains some elements, which we are mapping to another set, which is called codomain. For clarification of confusion, that is called as codomain.
Okay, not fully understood, but go ahead. Hmm.
Nodes also. Okay. At least then into function, at least one element in codomain has no pre-image. Range is a proper subset of codomain. F of n n arrow n f of x equal to x to the power of 2. Not all n are squares. Then bijective, one to one plus on to condition it has to satisfy. When this perfect pairing happens, both injective and subjective, in that condition, domain is equal to codomain. If you contain A as a set of natural numbers and B as set of natural numbers, how the bijective is, it should be equal to domain and codomain. If it's not equal, it could be any of these four. This is the important function formulas. The student need to memorize these also, and on this the gate problems can be asked for basic derivation, like deriving element, deriving number of elements, deriving the functions and all. This total on to they can note it down also. This the shortcut. We don't have time to. We may not have time to solve every problem in detail. So please note down the shortcuts also and remember the conditions also. This composition of function, composition g of f a equal to c, where g of f x is equal to g of f of x. Apply f first, then go to g function. Composition properties. This is the theory part, all are theory part. Composition is not commutative. Like f of g is not equal to g of f in general. Like you can say that 1 plus 3 is equal to 4. Also 3 plus 1 is now equal to 4. But in composition of function, it is not commutative in general. Composition is associative. F into g into h is equal to f into g into h. Like 2 into 3 into 1 is 6, and 1 into and 2 into 3 into 1 is also correspond to 6. That associative property here is applied. If f and g are bijective, then g of f is also bijective because both sets satisfy bijective condition. Then G of f is also satisfy bijective condition, as you studied in second PO and all. If you have forgot it, I will include that also. If G of f is injective, then f is injective. If G of s is subjective, then G is subjective. In our function, this I think some set text is, yeah. Okay. Inverse function, this is f of f to the power of minus 1 exists if and only if this, if you consider if and only if f is bijective. If f of a maps to b is bijective, f of f to the power of minus 1 is b mapped to a. F of f to the power of minus 1 into f of x is equal to x, and f into f to the power of minus 1 into y is equal to y. This is called inverse function. This that it's they can students can also implement to for identification and common types of trap that to ignore. If they revise this also, they can easily score some good marks and clear out their confusion. So revise this. Moving on to partial orders. Okay. What is partial order set? Partial order means order which is very partial. Set means partial ordered set is a set A together with the relation is reflexive and symmetric and transitive. This here where we studied about equivalence relation, which it contains. It says that it has to be reflexive, symmetric, and transitive. But here in a partial order, the only difference is it should be reflexive and transitive, but it should be antisymmetric. That's all. The three pillars of partial order are reflexive, antisymmetric, I said, and transitive. If you forgot to uh, map that condition, you can see here. The classic poset examples are natural numbers with usual, less than or equal to ordering, then subset of A, power set with subset relation, and N or natural numbers with divisibility. A divide B means A divides B here. Moving on to Hasse diagrams. These are the rules. Remove self roots.
Why are
Remove
they
adjust.
called Hasse diagrams?
Because Hasse diagrams means in
Is it the
mathematics.
name of a person?
Uh,
You can tell in the
let
next class.
um, as far as I know, this Hasse diagram.
You can tell in the next class. Ashwin.
Yeah, sure. Thanks for the doubt. I will let you know, sir, and students. These are the rules for the Hasse diagram construction. You can just note it down. Usually they ask the question based on this, but you should be able to construct also. Use this. Okay, this is the Hasse diagram of poset 1, 2, 3, 4, and divide division relation. If you
Sorry,
apply these
what is POSIT? Like POSIT is a short form for something.
partial order set, sir. Partial order
Partial
set.
order set, is it? Okay, okay.
Here you can see, right?
Mm-hmm. Okay.
Yeah. Yeah, for a long name, we have a short name is called poset. This is the Hasse diagram based on these rules, and implementing this, we contain this. Minimum element is called minimal and 12 and maximal. These are the mapping that made by that divisional rules and the structure also you can see here. One at the bottom, it divides all the elements. So that's why it is considered bottom in one. Minimal element also, that's 4 covers 2 and 1. That's why 6 covers 2 and 3, as you can see here. And 4, 12 is at the top. It is divisible by these all numbers. Maximal element. This is the here 12 is the maximal element. Then minimal element. Minimal element is 1. Greatest top of element. It's also greatest top of element here. Then least element, bottom. You can say that these are these are not distinctive, but it is distinctive at the when you solve the problems. It is distinctive. For condition, it say that it's distinct. It's, condition, it may seem same, but it's distinctive. Key is maximal not equal to greatest. Greatest element is maximal, but not vice versa. A partial order set can have multiple maximal elements, but at most one greatest element it contains. Like if you consider set 1, 2, 3, 4, 5, there 5 is the greatest element. It may or may not be maximal or vice versa. There's chains and anti-chains. This orders of within the partial order. A subset, you can see the definition. A subset C where every pair of elements comparable for all A, B in C, either A less than or equal to B or B less than or equal to A, which is called as chain. Moving on to anti-chain, a subset where no two distinct elements are comparable for all A, B, they are incomparable. Like here in this condition, A is less than or equal to B or B less than or equal to A, but in anti-chain it's not comparable. Total order is a percent with every pair of elements is comparable. That comparable order is the total order for total. The example is the maximal chain, for example for anti-chain and larger anti-chain. This called please note down Dilworth's theorem also. In any finite process, the minimum number of chains to cover all elements equal to size of the maximum anti-chain. These are the previous year questions they can solve. Moving on to lattices.
So one question,
Uh,
Ashwin, in which year did you study discrete mathematics?
in discrete mathematics, I usually studied in in engineering times. I studied in like fifth sem or fourth sem, I guess. No, fourth sem or fifth sem. In few times I studied this in second PU. But these chains and anti-chains were mentioned, but not in
And
detail.
who was the faculty for when engineering for you?
Um, and his name is Prashant, sir.
No, no. In engineering, from Department of Mathematics, who took this subject?
Reshma ma'am.
Reshma. Okay, okay. Yeah, thank you.
Uh, Not Reshma ma'am. In ground floor, the where the usually the department is there, not the department of AMS, where the another Reshma ma'am was there. I will let you know
Okay.
them
Yeah,
when
yeah.
I come.
Okay, go ahead.
This is a previous question. If you memorize all the problems, all the formulas and the condition, you can solve these all. Moving on to lattices. What is a lattice? Lattice is a poset in which where every pair of elements has both with upper bound LUB The LUB is least upper bound, and GLB weight is lower bound. The two core operation are AVB. That's not V, but this is the least upper bound. Represented least upper bound is considered this symbol. This symbol considered least upper bound. Join. This is the smallest element where it is greater or equal to both A and B. That greatest upper bound, largest element in A less than or equal to both A and B. GCD in example is LCM in divisibility lattice and GCD in divisibility lattice. 4 is 6. LCM of 4 is 6 is 12. And upper bound is 4. For GLB 6 is GCD of 4, 6. It is 2. If you calculate this all, you get this, and this is called lattice. The properties, this slide corresponds to properties of the lattices. Sorry, this properties corresponds to lattices. The key insight is power set lattice uses union as join and intersection as meet. This is a Boolean lattice. That power set lattice, Boolean lattice is the example. These are the types of lattices: complete lattice, distributive lattice, complementary lattice, and Boolean lattice. Boolean lattice, as mentioned, lattice both distributive and complementary. Must have two power of n elements. These are the conditions should satisfy to be a particular type of lattice. The hierarchy is Boolean subset complemented and Boolean subset distributive. Not all distributive and complemented are, and vice versa. It should be one of them. Then comes Boolean algebra and lattices. This various operations that mentioned, you can see there. Then the get previous year question, you can solve that according to when you solve the problems and the example problems. You can solve these also. The common mistake which and the explanation also you can see here. Common mistakes in gate that student make is symmetric and anti-symmetric confusion, maximal and greatest element, Hasse diagram errors, functions and range, and counting subset with the proper subset. Please avoid this and please etch into your mind. The shortcut revision sheet, formal summary, next practice question for reference. This is the Viva questions. You can just remember. Then the concept map here the discrete mathematics is set theory, partial order. This just a sub concept. This is the main concept today's for today's session. Okay, till now this is a
Thanks a lot,
preparation one.
Ashwin. Very, very good session. Very productive.
Yeah.
But of course, for me, most of the things have, gone over the head. Okay. But thank you
Okay.
very
Okay.
much. I'll stop recording now.